Let me begin by saying thank you very much to the organizers for the invitation. My talk today is going to be on punctures for theories of class SADE, and it's based on this paper with these collaborators. So to begin, I'm going to review class S theories, their construction, and their punctures, and then I'm going to do the same thing for these new theories of class SADE. So for class S, the relevant 6D theories arise as the world volume theories of M5 branes. If I take a stack of n M5 branes, I get the 2, 0 SCFT of type AN-1. If I take this theory and I compactify on a punctured Riemann surface, I get what's called a class S theory in 4 dimensions. These theories have n equals 2 supersymmetry, and they were famously studied back in 2009 by Gallardo. Today we're interested in punctures. So one way to get at the punctures for these theories is to deform the geometry by taking this puncture off to infinity so that the resulting geometry looks like S1 times R plus. Classifying the punctures therefore amounts to classifying the allowed boundary conditions for the fields on this space. So that's what we want to do. First of all, we're going to reduce on S1. And when we do that, we get a 5D quiver theory that looks like this. Written in terms of 4D multiplets, we have a chiral, an anti-chiral Q tilde, and a vector sigma all in the adjoint. We're going to set Q tilde equal to 0, and we're going to impose F and D term constraints to preserve supersymmetry in the 4D theory. When we do that, what drops out are simply Nahm's equations. Next, we're going to take sigma and Q to have simple poles. This restricts us to the so-called set of regular punctures. And when we do this and plug it into Nahm's equations, we get simply an SU2 algebra. This means that regular punctures are classified by solutions to this SU2 algebra, which are in turn classified by partitions of n. So we reproduce the well-known result that for class S theories, regular punctures are labeled by partitions. And now we want to do the same thing for these theories of class SADE. Here, the relevant 6D theories arise when you take M5 branes to probe an orbifold singularity. If you have n M5 branes probing an orbifold singularity of type A, D, or E, respectively, you get n-1 copies of the gauge group G, which is of A, D, or E type. We're going to take this 1, 0 theory in 6D, once again compactify on a punctured Riemann surface. Now we get what's called a class SADE theory. This has half the supersymmetry, and the study of these theories is really in its early stages. Once again, we can consider the punctures by deforming the geometry, looking at the boundary conditions on this space. We perform the S1 reduction. Now we get a slightly more complicated quiver. For the A, D, or E type theories, we respectively get the A, D, or E type Affin-Dinkin diagram. We can impose the F and D term constraints once again to preserve supersymmetry in 4D. And what drops out are a set of generalized Nahm's equations, which you can find written in our paper. So we've come up with a couple of methods for solving these generalized Nahm equations. The first one is the Douglasmore approach. You can embed the n by n matrices Qi and sigma I in these larger Kn by Kn matrices. And when you do this, the generalized Nahm's equations simply become the ordinary Nahm's equations with this additional projection condition, where here you should think of gamma as some matrix that enforces this projection. So this means that the solutions are once again going to be labeled by partitions coming from the SU2 algebra, but now with some additional labels indicating the action under gamma. So for instance, for n equals 2, k equals 4, we get these two punctures, these two different solutions. They correspond to the same partition, but they're different punctures because of these different labels. The second method we identified was to re-express these partitions in terms of directed graphs. So for instance, this solution here can be written as this directed graph on the nodes of the quiver. And you might wonder, how is this buying us anything? Well, this partition language works well for the A and D type cases, but for the E type cases, you actually need to go over to this directed graph approach. So for instance, for E6, you get a solution that looks like this. So this is a puncture for the E6 theory. Time constraints permit me from saying anything more, so let me summarize. We've seen that compactification of 61, 0 theories on punctured Riemann surfaces yields these class SADE theories. We've identified special classes of punctures for these theories, but there's much work still to be done, both in terms of a complete classification of punctures, as well as understanding these theories in more detail. Thank you.
One question? Okay. There are no questions. Let's thank Thomas again.